Hello, everyone. Today I'm going to talk about the important, interesting concept in machine learning, which is embedding. So embedding is very useful in machine learning. It's widely used in a lot of different fields, including the text, graph, recommendation systems, and things like that. And also with embeddings, we can build the multimodal models that can actually take care of different kind of inputs with different modalities. And I will show you one example, which is CLIP, which is very popular model that the can take also take both text and image as inputs, and also output the embeddings that can like take care of different kind of input data. So let's get started. So the first thing I want to talk about is the main idea of embeddings. So why do we need embeddings in the first place? So the embeddings is important for machine learning models because you know that machine learning models take need to take the numerical data as inputs. It cannot take the raw images or raw text as inputs. So first, we need to convert the word or images into a numerical representation. So what numerical representation is good? So as we know that the in neural nets, we have a lot of matrix transformations on top of the on like applied on the vectors. So it's like matrix vector multiplication. So therefore, a best representation, numerical representation for input data will be a vector representation, such that the matrix can directly apply on that. So we need to convert it. We need to convert all images, all text images, all different kinds of inputs into a vector like this. And the second reason why we need the embedding is that we wanted to, the embedding itself has some semantic meaning. For example, in the graph here, we basically embed different kind of input data into the same embedding space. And we can see that the data with the similar semantic meanings are closer to each other in the embedding space. For example, the road here, the car, and also the image of a car. So they are like very close to each other. And these are all the like inputs related to cats, including a sentence for cats and also the image of a cat. So they actually group together to be a like close to each other in embedding space. So that's the second reason why embeddings is important. So let's look at a concrete example of embeddings. So we take embedding for word here. So we can see that each word is mapped to a high dimensional vector, and each dimension can represent a specific properties. So for example, here, the first dimension represents animal, whether this word like is related to animal. And the second dimension could be like whether this is like newborn or not. And also third dimension, whether this human. And this dimension says whether this word is the plural or singular. So for example, if we look at cats, okay, so it's an animal, so it has a very high score in this dimension. It's not newborn, it's not necessarily newborn, so it's like having a close to zero values in this dimension, and also it's not human, so this score is low in this dimension. And it's plural, so it has high score in this dimension, and also it's not true, so it has negative score in this dimension. And similarly, we can look at other words like puppy, houses, etc. So for example, of puppies, we can see that it has a pretty high score in a newborn because it's related to like newborn dogs. Okay, so yeah, so I would say each dimension represents a specific meaning or specific properties of a word, and all these dimensions together encode the semantic meaning of a word. So that's the idea for word embeddings. Okay, so how do we actually get the word embeddings? We know that the like one of the first idea, one of the first models for embedding is actually useful word, which is the word to vec embeddings. So 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 how do we actually calculate that? So here we use the idea that if two words are close to each other in in the sentence, those two words should have similar embeddings in embedding space. Okay, so to do that, so first we need to figure out what is the like what do we mean by two words that are close to each other. So to do that, we actually need to use a sliding window like this, and we say that and in the sliding window we have a center word here. In this case, it's not center word here, and the word in the sliding window. So these words in the sliding window are close to the center word not. So we say that this word not should have similar embeddings with its neighboring words. Okay? So we can use the word not to form a positive pair, form positive pairs with its neighboring words. So as we see here, the word not together with these neighboring words here, they form positive pairs. Okay? And also we can form negative pairs by using a specific word and together with any word that outside its neighboring words, outside its like neighboring neighborhoods. So these words will form negative pairs. Okay, so once we have these samples of positive pairs and negative pairs, we can do the following. We take a pair of words, for example, in this case, these two words, and we map them to embeddings. And then we pass the pair of embeddings to a neural nets. So the task of this neural net is to predict, okay, are these two words neighbors? If they are positive pairs, then the output should be like, yes, they are neighboring words. If they are negative pairs, meaning that they do not appear in the same neighborhoods, then the model should say, okay, so this is not a positive pair. They are not neighbors. Okay, by doing this, the model will figure out a way to encode embeddings, to encode this embedding such that the neighboring words are more likely to be similar to each other, and the non-neighboring words are like have very different embeddings. So that's how we get word to vector embeddings. So how do we actually understand this representations? So previously we have showed examples of like different embeddings for different words, and we say that each dimension represents specific semantic meanings. And how do we utilize this kind of semantic meanings? So this is a very popular example of showing how we actually interpret and like how do we interpret and utilize this specific semantic meanings along different dimensions. So here we say that there are two different dimensions encoding encoding different aspects of the words. So this along x-axis, this dimension represents the gender, so whether it's male or female, and on the y-axis, it says whether this word is related to a royal family or not. Okay, so with this different kind of in this 2D space, gender, royalty, 2D space, we can do a bunch of semantic manipulation of the words to get a new word. For example, if we start with this word man, if we move the word along x-axis, along the gender axis, we can transform the word man to woman, basically by transform the word from male to female. And if we move the word along the y-axis, which is the royalty axis, then we can make the word to be related to a royal family instead of the original word man. We get actually get a new word king, which is related to royal family. So what I want to show here is that because the embedding have like specific semantic meanings along different dimensions, we can actually do semantic manipulations in the embedding space to like get the new words and also get to figure out the meaning of different words. So this is just a simple example. We can do some other more complicated things. For example, there's a way to figure out what will be the capital for each country and so on. So all these manipulations can be done in embedding space. Okay, so once we figure out the word embedding, a natural extension is to do the sentence embedding. So the idea is pretty much similar. So previously in the word embeddings, in the word-to-vec models, we use the contrastive learning idea, which basically is to find positive and negative pairs, and then like pass the corresponding pair of embeddings to neural nets, and then the results should predict whether they are a positive pair or negative pair. So similarly, for sentence embedding, we use the same idea. So first, we need to have a pair of sentence, okay? And then we pass the pair of sentence to a model. In this case, we're using the BERT model. And then after that, we do the pooling operations, and then we get a sentence embeddings. And this sentence embeddings are used to predict whether the words are, whether the sentences have the same meaning or not. Okay, if they have the same meaning, we require that their embeddings should be close to each other, should be similar. Otherwise, if they are not, like they do not represent the same meaning, for example, in this case, the first sentence talk about gravity, the second sentence talk about the color of sky, so they do not represent the same meaning. So we want to make sure that embeddings are not similar to each other. Okay, so by doing this, we can actually get the embeddings for sentence using the same idea of contrastive learning. Okay, so after we talk about the text, embeddings are also used in other fields. For example, it can be used in graphs. So here we talk about, we show the example of the embeddings for finding the embeddings for graph nodes. Okay, so on the left-hand side, we have a graph. So there's a bunch of nodes and a bunch of connections between different nodes. And the idea of finding graph node embedding is that for each node U, we want to map it to a high dimensional vector. So in this case, d-dimensional vector. So that vector can be later used for downstream tasks like graph node classifications and graph node and things like that. So because we know that we have a good method to get embeddings for word, which is word-to-vec. So the problem is, is it possible that we convert this problem of finding the graph node embeddings to original problem of finding embedding for words? So here there's idea of node-to-vec. It is idea based on the previous word-to-vec. So we need to find so as a first step to convert a problem of finding node-to-vec, of finding the node embedding to finding the word embedding, we need to figure out what is the sentence in the graph. Okay. So to find such sentences, we can use the random walk on the graph. For example, given this graph, we can run the simulation of multiple random walk. So each random walk will start with a random node, for example, A, and it can go either to B or C. In this case, we can go to B, and then it can go to D, and then can go to E. So this is one random walk path, and we can repeat this kind of random walk multiple times such that we get a sentence of corresponding for different random walk. So for example, in this case, we have 3 sentences. The first sentence is A, B, D, E. second one is A C D E, and third one is A B C D. Okay, so once we get this random walk, then we have a bunch of corresponding sentences, and so and the word here is just the node. So each node is like similar to a word in the sentence. So we can take a like comparison here. So in text, the unit of text is token or word, and for graph, the unit is node, and the sequence of the text of the words is just sentences. And here, the sequence of the random of the graph is just random walk path. So by taking this analogy, we can see that we can apply the idea of word to vec to graph nodes to get the node to vec. So we can use a very simple idea of getting the like positive pair, negative pair, and based on the labeling relationships, and then discover what will be a good embeddings for each node. Okay, so that's for node embeddings. And then we can switch gear to a different domain, which is the recommendation systems. So in recommendation problem, we have we generally have a input as the ratings matrix. So in the ratings matrix, we have the following. So each user will have a preference rating for each item. So for example, this user, the first user, has a high rating for Harry Potter's Wreck and Dark Knight Rises, and has like no rating or negative rating for others, and thinks that, and we have a bunch of other ratings for different other users. So to find the prediction of the recommendation score for a new user on a new item, we can also use the idea of embeddings. So the idea is as follows. We want to have two sets of embeddings. So one set of embedding is for users. So for each user, we want to have a embedding for that user. For example, for this person, we want to have this embeddings to represent this user. Also, for each item, for example, for this item, we want to have an embedding for this item, so that we have two sets of embeddings, one for user, one for item. And then we can say that the recommendation score is just the inner product between the user embedding and the item embedding. So why is that the case? So imagine that the user embedding. So to understand this, we can actually say that each dimension of the user embedding represents a specific property, and each dimension of the item embedding also represents a corresponding property. So if the user embedding has a pretty good alignment with the item embedding, their inner product will be high, then we can say that, okay, so this user will be likely to have a high embedding, high rating for this corresponding item. So for example, if we take like two-dimensional embeddings, then the one dimension could be that, okay, so this movie is for is this user has preference for either action movie or romance movie, and a second dimension could be like this user has preference for either comedy or serious movies, and similarly, the items will have embeddings saying that, okay, so this movie is for action or for romance, and second dimension could be, okay, this movie is like more related to comedy or it's more serious. So for example, if the user has embedded 0.9, 0.1, then okay, so this user is likely, so it's very likely that this user loves action and not so much into comedy. And a movie vector 0.9, 0.2, meaning that it's action heavy and not very funny. So we see a good alignment here. So their dot product is very high. So system predicts values, predict that this user will like the movie. So yeah, so the point here is that um, we can get the set of corresponding user and item embeddings, and then we can use their inner product to like as a rating score to see whether this user will like this movie or not. So that's the application of embeddings in recommendation system. There's a lot of other ways to use embeddings in recommendation system. For example, instead of taking the inner product, we can actually take take the user embeddings together with the item embeddings and pass those two embeddings to a neural net and predict their rating score. So that is another way to do that, and that is in some sense a better way to do that, because in that way we can incorporate other information about users and items, not just the simple embedding information. But again, embeddings play a very important role in these kind of recommendation system algorithms. Okay, so our previous examples, we only show that we can do like we can use embeddings for one modality inputs. So for example, in the word to vec or sentence embeddings, we only take the text as inputs, and in the graph nodes embeddings, we only take graph as inputs. In the user item embeddings, we only take the ratings matrix as inputs. So all of these have only one single modality. But in practice, we want to do a multimodal models that can take multiple modalities. For example, in this case, we want to take both sentence and image as inputs to the system. So to do that, one way to do that is to use the model shown here as a clip model. The idea is that instead of having a one encoder to map the input to one embeddings, we can have two different encoders to take care of two different modalities. So for text, we have a text encoder, so that it will be mapped into an embeddings, sentence embeddings here. And for image, we can take we can use an image encoder, which is, for example, we can use vision transformer, such that the image can be converted into an image embedding. So once we have a pair of sentence and image, as we usually do, we can actually have a pair of embeddings as like in the intermediate layers, and then we can use these pairs of embeddings to like get the output score, saying that whether the pair of inputs are similar or different. If they are similar, the output score should be 1, otherwise it should be 0. Again, this is the idea of a contrastive learning. The idea is that first we build the positive and negative pairs, and then we get the embeddings corresponding to the pairs, and then we get the output saying whether the pairs are similar or not similar. If they are similar, the embeddings should be similar, should be close to each other. Although they come from different modality, their embeddings should be similar. Okay, So that gives us very important way to take care of different modality, different like modal data. Um, so this is very powerful, and also there's a lot of different extensions and generalizations of these methods. For example, in some models, it can actually take a user adapter, such that you taking a sentence, you taking the image, you can pass the image through a modality adapter and convert it to a specific embeddings that can be used for the language models. So yeah, there's a different ways to bridge the gap between different modalities. So that's a very important way to use embeddings because in a lot of models like ChatGPT, sometimes we want to input not only the text but also we want to input images, and also sometimes we want to provide the image and we want to get the caption of the image, and also we can do something different. We can putting a description of a sentence of the image, and we want to ask the model to generate a new image based on the description. So all these tasks require to have a multimodal models that can actually take care of embeddings for different types of inputs. So that's pretty important and pretty powerful. Okay, so that's pretty much everything we want to talk about. So so the main takeaway here is that embedding is a like universal. We can see embedding as a universal encodings for different kinds of inputs that can be like very useful for machine learning to to process. It not only encode information in a very simple and very elegant way, but also it can bridge the gap between different modalities, such that the model can take care of different kind of inputs. And with these embeddings, the machine learning model can actually understand the abstract data and convert everything, compress everything into a vector, such that the encoded information can be used to downstream tasks. So it's fair to say that embeddings is one of the most important discoveries in machine learning, and it's widely used in different fields. Thank you. Let me know if you have any questions, and thank you so much for your attention.